Now we are going to discuss about a new term called as entropy. For that, we will need to begin with the famous Clausius theorem or Clausius inequality. It states that for every thermodynamic process, integral over dq by t is less than or equal to 0. Using the same inequality, we are going to define the term entropy. Entropy is denoted by letter S, and for any process, any thermodynamic process from A to B, suppose during this process an infinitesimally small amount of heat dq either enters the system or it leaves the system. Both way it is possible. Anyway, there is a change in heat dq associated with the process, and the process happens at temperature T. Then the corresponding change in entropy of the system, ds, is defined as dq divided by T. So the SI unit of the term entropy is going to be joule per Kelvin. Since joule is the SI unit of heat, that is energy, and Kelvin is the SI unit of temperature. This is how we have defined the term entropy. Now, in this Clausius inequality, this less than sign holds true for all the processes, whereas equal to sign holds true for reversible processes. Another thing to note is that if a process is adiabatic in nature, when the process is adiabatic, no heat is allowed to enter or leave the system. So for an adiabatic process, change in heat is always 0. So accordingly, the change in entropy is also going to be 0 for an adiabatic process. This thing we have to remember. Now we will see whether the entropy is a state function or a path function. For that, just imagine a reversible cyclic process where a system goes from point A to point B by taking some path A, and then it returns back from point B to point A by taking some another path, say path B. Now this process is reversible and cyclic. Reversible and cyclic. So the corresponding change in entropy, as we have already defined, is going to be integral dq by t. Now this integral can be written in the following manner: integral over path A dq by t plus integral over path B dq by t, where system goes from state A to B, and in the second case system goes from state B to state A. Now we should note that since this process is reversible and cyclic, the change in entropy is going to be 0, as is the case required by Clausius inequality. So this integral is always going to be 0. So this means that integral A to B dq by t by following path A is equal to minus integral B to A dq by t by following path B. So now this integral can be reverted, the limits can be reverted on the right hand side. So this is now equal to A to B. The minus sign is absorbed and the limits are changed from B to A to A to B dq by t following path B. Here we see that change in entropy by following path A is same as change in entropy by following path B. So even if the two paths are different, the change in entropy for path A is same as change in entropy for path B. So this proves that entropy is not a path function, but it is a state function. That is, instead of state B, if there had been some other state C, which is quite different than B, then this entropy would have been very different. So entropy is purely a state function and not a path function. This is a fundamental property associated with entropy. Now, as an exercise, just try to understand the Carnot cycle, which we have already studied, using a temperature entropy diagram. Temperature entropy diagram. So, just for a comparative study, let us redraw the Carnot cycle as it has already been studied. So, A to B, if we remember, heat Q1 is absorbed, and this process happens at constant temperature T1. So this process is isothermal. From B to C, this process is adiabatic. From C to D, the process is again isothermal and happens at temperature T2. And amount of heat Q2 is rejected during this process. And D to A is again adiabatic process, which is a compression. So this is adiabatic compression. B to C is adiabatic expansion. Now the same process could be represented on a temperature entropy diagram. So let us start from point A. Note that this process is isothermal, so it happens at constant temperature. So in this case, if this happens at a constant temperature T1, we should draw a horizontal line here starting from A and ending on B. Now from B to C, the process is adiabatic expansion, and we have already seen that for an adiabatic process, change in entropy is 0, so entropy has to be constant. That is the meaning of it. So similarly, for a constant entropy, we should draw a vertical line starting from B and ending at C. We should note that temperature decreases from a value T1 to a value T2 during this process, since it is an adiabatic expansion. So the new temperature reached is some lower value T2. Now again, process C to D is again an isothermal process. So we draw this curve from C to D, and process D to A is again adiabatic, so it implies that entropy remains constant. So a vertical line is sufficient to represent it, and system returns back to point A. Now the same process is represented on a CV diagram, sorry, the TS diagram. This was on a PV diagram, so pressure versus volume, and this is the same Carnot cycle represented on a TS diagram, temperature entropy diagram. Now we should note that amount of heat Q1 is entering the system here, amount of heat Q2 is leaving the system here, whereas from B to C and D to A, the process is being adiabatic, the amount of heat entering or leaving the system is 0. So here no heat is involved, or no change in heat is involved, so delta Q should be 0 in these processes. So if we try to recall Q A to B, then if we have the definition, ds is equal to dq by t, so dq is going to be t into ds. So if the temperature is constant, we can just integrate it, and we say that delta q is t delta s, right? So in that sense, for process A to B, we have T1 into SB minus SA, that is change in entropy, that is entropy at point B minus entropy at point A. Similarly, Q B to C is going to be 0 since the process is adiabatic, no change in heat is involved. Then Q C to D is accordingly T2 into SD minus SA. SD minus SA. Now we should note that SD is the same entropy at SA, and SB is the same entropy at point C. So This SD is nothing but SB minus SA, correct? Because SD, point D and point A both are having the same entropy. Then for process D to A, again the change in entropy, the change in heat is 0 since the process is adiabatic. This is the amount of heat entering the system. This is the amount of heat leaving the system. Now, as per the earlier definition of entropy, eta is Q1 minus Q2 upon Q1, which is equal to 1 minus Q2 upon Q1, which is equal to 1 minus, let us just substitute the values of Q2 and Q1. Here we have T2 into SB minus SA divided by T1 into SB minus SA. So these terms get cancelled and we are left with the expression for efficiency as 1 minus T2 upon T1. As we have already proved the same relation using the traditional way of analyzing a Carnot cycle on a PV diagram. So yes, we can also derive the same relation using the concept of entropy and with the help of a temperature entropy diagram. And it provides a very shorter way for the derivation as compared to the traditional way. We will explore other facets of thermodynamics related to entropy in forthcoming lectures. Thank you.